Hello, my name is Daniel Mahecha. I am a graduate student at Universidad de los Andes in Bogotá, Colombia, and I will show you our project titled Machine Learning for Improved Prioritization of Variants of Uncertain Significance. Genetic disorders like hemophilia, muscular dystrophy, and cystic fibrosis affect more than 300 million patients worldwide, causing high rates of disability and premature death. An additional problem is the diagnostic delay for many of these disorders, which can be as high as 30 years. The diagnosis of genetic disorders starts with the clinical suspicion. Then we usually perform selected gene panels as first-line tests. If the result is unsuccessful, we carry out whole exome or whole genome sequencing. However, these high-throughput sequencing technologies have shown to be cost-efficient as first-line tests for many disorders as well. One of our greatest challenges on genetic diagnosis is the high proportion of variants of uncertain significance, especially in non-Caucasian populations like ours. In fact, the rate of VUS in our pool of patients is 70%. This is very inconvenient for medical practitioners and patients who don't want to have even more uncertainty on their diagnosis. To help us resolve this VUS, we wanted to create a model to prioritize those variants with a higher probability of being pathogenic. We checked current predictors of variant pathogenicity or deleteriousness, and we found that most focus only on missense variants. Also, on the chart we can see the distributions of the scores of three of the most widely used tools. Some of them overestimate the pathogenicity of benign variants. Others have more uniform, but presumably less informative distributions on the sets of variants of uncertain significance. So our goal was to create a model able to handle different variant consequence types and which also yields improved performance on our VUS. To build the models, we selected from ClinVar variants that were not classified as VUS and had more than 2 quality stars, meaning multiple submitters, assertion criteria provided, and no conflicts. We created a special set of XVUS for further testing, selecting a group of about 400 variants that were VUS in October 2017, but had been reclassified in any of the other 4 categories 2 years later. We used the remaining variants to train a random forest, a support vector machine, and a 5-layer perceptron, and we tuned the hyperparameters to optimize the area under the ROC curves. We merged the benign and likely benign variants into one unique benign category and the pathogenic and likely pathogenic variants into a unique pathogenic category. As features for the models, we used 9 conservation scores, the loss of function tool, and variant consequence types. We also wanted to assess if we should use allele frequencies from the 1000 Human Genomes Project global dataset. As seen on the chart, most pathogenic variants had absent values, but when we used the allele frequencies on preliminary tests, they improved model performance, so we kept them as features for our models. After building our models, we used our XVUS set to test their performance on our VUS, on the VUS population. In the pie chart, we see that about half of variants are missense type, and there are also synonymous, non-coding transcript exon type, intron splice variants, and other variant types. On the ROC curves, you can see that our highest performing models were the random forest and the support vector machine, with an AUC of 0.92. You can also see cats with an area of 0.98. Rival and Polyphen are shown as reference of tools for missense variants only, which consequently have lower areas if we take into account all the consequence types. So, to make a fairer assessment of our performance across different variant types, we plotted AUC curves on other types as well. Here we see our performance on missense variants, where we got an AUC of 0.93 for the random forest. The rebel score is close with an area of 0.92. For other variant consequence types, performance of our models is competitive too, and the random forest gets slightly higher AUCs. Finally, we run our models on a set of CleanVar variants, currently classified as VUS. Approximately 2/3 of these variants are predicted to be pathogenic, and 1/3 is predicted to be benign. All models have HR peak and values of probability of pathogenicity close to 1, and the random forest and DSVN have a less marked peak in values close to 0. In conclusion, we were able to create one-fit-all models to help resolve the high proportion of VUS in our patient population. We are currently integrating the models on analysis pipelines of real data from our patients. We hope that our models will be useful for other researchers working on genetic diagnosis. We want to acknowledge CIGEN for its financial support and Fabián Heredia and Jessy Ramirez for their help on the initial stages of this project. We will be happy to answer your questions and get your feedback. Thank you.